So if we have something in exponential form like 2 to the 4th equals 16, we can rewrite that as log base 2 of 16 equals 4. Likewise, if we have log base 3 of 9 equals 2, we could rewrite that in exponential form as 3 squared equals 9. So we can use the property log base b of a equals x is the same thing as b to the x equals a. So we can just rewrite those things. Now let's do 9 or 10, I guess, really quick practice problems along those lines. So log base 2 of 64 equals x can be rewritten as 2 to the x equals 64. Log base 7 of x equals 2 means 7 squared equals x. Log base 6 of x equals 3 means 6 to the 3rd equals x. Number 4 can be rewritten as square root of 3 to the 0 equals x. 5 is 3 squared equals x. 6 is 2 to the 3rd equals 2x plus 1. 7 is x squared equals 4. 8, if we understand what natural log is log base e. So we have log base e of e to the x equals 5. So if I rewrite this, I get e to the 5 equals the part on the inside, e to the x. This is 3 to the 2x plus 1 power is equal to 243. And this one is actually in exponential form. So this was the only one out of these 10 that's in exponential form. So we're going to rewrite it in logarithmic form. That would be natural log of 10 equals 3x when we take the natural log of both sides. Now, I know it says to solve them, and I didn't solve any of them. So a lot of these are just kind of understanding what's happening. So if I realize that 2 to the x equals 64, x would equal 6, because 2 times itself 6 times gives us 64. 7 squared is 49. 6 to the 3rd, or 6 cubed, is 216. Anything to the 0 power is 1. 3 squared is 9. 2 cubed is 8, so we have 8 equals 2x plus 1. So x equals 7 halves. X squared equals 4 means x equals plus or minus 2, but we also have to be careful because the base of a log cannot be negative. So the answer is actually only x equals positive 2. So if e to the 5 equals e to the x, then x has to be 5. 243 is really 3 to the 5th. So then I can just recognize that 2x plus 1 equals 5, since the exponent 5 has to equal the exponent 2x plus 1 if both bases are 3. So x equals 2. And over here, x equals natural log of 10 divided by 3. So I know I just did those 10 problems real fast. In terms of finding inverses, we'll actually do this both ways. So if I have a function log base b of x equals y, in order to find an inverse, I'm going to flip the x and y and solve. So in order to get rid of log base b, I'm going to take b to the power of both sides and rewrite it in exponential form. So b to the x would equal y. So the inverse function over here would be y equals b to the x. So notice that inverse function of a log is an exponential. And over here, I would flip the x and y. And then in order to get rid of the exponent, I could take log base a of both sides. Log base a of a to the y is just y. So notice The inverse of an exponential function is a log function. The inverse of a log function is an exponential function, which makes sense since there's this equivalency property that I can rewrite things. Now let's do two quick practice problems. First one is 5 to the x minus 1 minus 2. So let's graph that. That would be 5 to the x. So 0, 1, 1, 5, 2, 25. And then what's happening is my x values are getting moved to the right 1. My y values are getting moved down 2. So if I rewrite these points, I'd be at 1, negative 1, 2, 3, and 3, 23. So I don't need the originals anymore. So I have these points on my graph. So 1, negative 1, 2, 3, and it goes up really fast since it's a 5 to the x type of problem. Notice that my horizontal asymptote typically at y equals 0 is going to get shifted down 2. So my domain is negative infinity to infinity. My range is, should be a parentheses, my range is negative 2 to infinity. So I put my horizontal asymptote on the graph. It goes up really, really fast. So that's my f of x. Now f inverse of x, I can graph this without really having to do any algebra because I know that the domain and range are just going to flip because all x values and y values just change. So the range is going to be negative infinity to infinity. The domain will be negative 2 to infinity. So I'm going to have a vertical asymptote at negative 2. And then my defining points will be all the x's and y's flipped. So negative 1, 1, 3, 2, and 23, 3. So negative 1, 1, 3, 2, and a graph that looks something like this, which, as we know by now, if I drew the line y equals x, it should look like the red and blue graphs flip over that. Now it's asking me to find f inverse of x algebraically, so I'm going to flip the x and y values and then solve for y. So I'm going to add 2 to both sides. I will then, that y has a really long tail. Then I will do log base 5 of both sides. So y minus 1 equals log base 5 of x plus 2. And then my f inverse function, which I've run out of room up here to write, is going to be log base 5 of x plus 2 plus 1. We'll do one more quick problem like that. Log base 3 of x minus 4 plus 1. So my initial function is a log function that has a right shift of 4 and an up shift of 1. So the defining points of log base 3 are typically 1, 0, 3, 1, and 9, 2. Then I will shift all of them right 4 and up 1. So 5, 1, 8, 2, and 13, 3, which of course is going to put us off the graph real fast. So I'll plot these points. Also note that it is a log function a right shift of 4. So my domain is going to be 4 to infinity. My range will be negative infinity to infinity. So there is my asymptote, 5, 1, 8, 2, and a lot of this is guesswork after that. Now, to find F inverse, I know that all of my points are going to flip. And I also know that my domain and range are going to flip. So I'm going to have a horizontal asymptote at y equals 4. I can graph the points 1, 5, 2, 8. And again, it's guesswork because we're off the graph pretty quick. But once again, if I graph to the line y equals x, it does look like the blue and the purple kind of flipped over that line. Then finally, I will solve for F inverse. So I will flip the x and y, log base 3 of y minus 4 plus 1. I'll subtract 1 from both sides. I will, that didn't really look like a 4. I will take 3 to the power of both sides. So that gets rid of the log on this side. And then we will solve for F inverse by adding 4. So I have 3 to the x minus 1 plus 4. And notice that's exactly what this purple graph looks like.